Cool. Right. So I'm going to talk about HTTP2. I've been interested in HTTP2 for a long time and been studying it and working with it to a certain extent. But probably a bit of background on me to begin with. I've been doing web performance on and off since about 1998, since the first .com boom. Left it for a while and then came back. Wrote a couple of books. The 5 Simple Steps one is a bit out of date. If you have it and you read the responsive images section of it, it's embarrassingly out of date. But I hope to do a second edition this year. Using WebPageTest is more recent. I spend quite a lot of my time in WebPageTest. One of my challenges at the moment is helping Pat, who runs WebPageTest, automate the installation to make it much easier for other people. But I work full-time in web performance. I deal with Britain's major retailers, Britain's major financial services, and as part of my role, I end up spending a lot of time looking at what affects web performance, looking at what's coming down the pipe, and what it means for our practices today. And so I've been interested in HTTP2 since it was speedy, effectively. I've been looking at this stuff for about 4 years. And we've got clients who are starting to deploy it via Akamai. And it's just interesting to look at, why do we need HTTP2? What's different about it compared to HTTP 1.1 that we've got at the moment? And what does it all mean for us as developers? What are the issues? And to start that journey, first of all, we have to step back in time. And we'll step back to 1999. Which was really the last time HTTP 1.1 was revised as RFC 2616. HTTP 1.1 was actually standardized as RFC 2068, I think it was, in 1997. But in 1999, Google was 1 year old. If you were working in IT, you were probably doing one of two things. You were probably working on this newfangled thing called the internet in the first .com boom, or you were working for a financial services company or somebody else with big mainframes, worrying about the millennium bug and whether our IT systems were all going to crash when the year 2000 came around. And as I said, the original RFC was 2616, but the web of 1999 was really, really simple. This is actually Yahoo from archive.org, the Wayback Machine from 1999. And we recognize it as a website, but it's mostly text. It's got a few images. We had no CSS here. If we wanted fonts, we had to use the font tag and the color attribute on images. We had low source on images. So that helped, with our responsive problems we've got today. But, this was the web of 1999. It was really, really simple. And this is why HTTP 1.1 worked really, really well for it. But the web of 1999 is not the web of 2016. We can look at Yahoo again, and we recognize the new Yahoo as being quite similar to the old Yahoo, but apart from we've got many more images. Our pages have grown exponentially. So the Yahoo of 1999 was probably a couple 100K at most. This is probably 2 megs. We have huge images. We have even colossal chunks of JavaScript that we send down the wire. So our websites have become much, much more complicated. The other thing that's happened to them is we've moved on from just building static websites to building experiences and interactive experiences. We have spreadsheets in Google Docs. We have things like Twitter that deliver real-time experiences. These are very, very different to what we built in 1999 when we originally standardized HTTP. And that gives some problems, because HTTP 1.1 doesn't use the network efficiently. HTTP runs on top of TCP, and TCP was originally designed to reliably deliver large files over long distances. And that's not what our web pages are made up of. Our web pages are made up of lots of little files, lots of little requests. And so what we've been doing over the years is hacking around these limitations. We've been working around the limitations of HTTP 1.1 without probably even realizing what they are or what we were doing to try and make our sites go quickly. And The first of these issues we have to deal with is that each TCP connection can only download one resource at a time. While that resource is being downloaded, that TCP connection is in use. If that resource is slow to download, that TCP connection is in use for longer. It's often referred to as, or it is known as, head of line blocking issue, where when we're downloading something, that connection isn't available for anybody else to download something on until our download is finished. So what browsers did is they went to this world where the original RFC said we could have two TCP connections. We could download two things at the same time. And Mozilla originally discovered that actually if you increase that number, if you went beyond 2, if you went to 4, things started to download faster. So other browsers caught on. Other browsers went to 4 or 6, or IE 11 will do 10 or 11 connections in parallel to try and make it so we can download more resources in parallel, so we can load our pages quickly. But that wasn't good enough. What we decided to do is, because 6 TCP connections wasn't good enough for us, we did like the BBC do here. We split our content over multiple hosts. So they have 4 hosts in this waterfall. This is a bit old, so I'm not quite sure what they do today. So they have 4 hosts in this situation. So if they can have 6 connections to each host, all of a sudden they've got 24 TCP connections they can use to download. Once they've got the base HTML page, they can download the CSS, the JavaScript, the images, to try and make the best use of that network, to try and make efficient use of that network to get that page up as soon as possible. But multiple connections and sharding across multiple hosts comes with a price. And that price is, sooner or later, we run into packet loss. We run into congestion on the network. It happens in many places. The routers we have on the network, our home ADSL or fiber to the cabinet router, which is, a piece of electronics that's built to a price point to be as cheap as possible, effectively, has a limited amount of memory. If it can't process the packets that are coming into it fast enough, it drops them. The routers out on the internet have exactly the same problem. They have a limited amount of memory. They're handling millions and millions of packets. And what happens is they get dropped, and we get packet loss. We get, in TCP terms, we get a collapse of the congestion window because we have to retransmit packets, and throughput actually goes down. So there's a trade-off between how do we split across multiple host names, how do we use lots of TCP connections, versus when do we actually lose data. The other challenge we have with HTTP is every request has an overhead. Every request we make involves a round trip, and that round trip is bounded by latency. It's bounded by about 2/3 of the speed of light is how fast is the fastest our network packets can travel. It's limited by the refraction index of a laser in a fiber optic cable. So at best case, our network packets travel at 2/3 of the speed of light. They often travel a lot slower than that. So what that means is, from here to New York is roughly 50 milliseconds. When our file transfers are split up into packets, our request goes out, we get our first response back in 50 milliseconds. Normally we'd roughly get 10 packets back. We then have to acknowledge we received those packets before the server will send us some more packets. So latency affects every single download we make on the internet. The other challenge we have is we have loads and loads of duplication in our HTTP requests. So typically every resource we request on a page has a bunch of headers with it. Those headers will often be repeated things. There'll be things like the user agent, what we'll accept depending on the resource type, who the referrer was. There's often cookies in there, and cookies are often 5K. A UK retailer who turns over about £1 billion a year online had a performance issue. And their pages were slow, and it wasn't their pages weren't optimized for download. What was happening is for every request they were sending a 5K cookie for it. So the base page had a 5K cookie. Every image on that page had a 5K cookie attached to it. Every CSS file, every JavaScript. And actually, the delay in sending, or the size of the request they were sending to the server on the upload connection was actually the thing that was the limit on how fast their page could load. Lastly, the overhead that we have with requests is TCP has this thing called congestion window. And the congestion window is how many packets we can send in a single round trip. It used to start off as 2 or 4. Modern Linux servers will send 10. So you make a request, you get 10 packets back. As long as you acknowledge each of those packets, in the next round trip, the server can send you up to 20. But in this case here, where we've got 10 packets and we've only sent 3, that means those 7 packets were wasted. If those are 1.5K each, which they are roughly, that's 10.5K we could have sent, and we didn't, and it has to wait for the next round trip. So they all add up. So, we have this overhead built into the network of the round trip, of the latency of the round trip, of the overhead of headers, and how well we actually use the connection. And what we've been doing for probably the last 10 years, since Steve Souders wrote his first book, is following recipes about how we make websites faster. And we may not always understand why we follow those recipes or the implications of what comes with them. So, one of the first recipes we follow is concatenate things. Merge our small CSS files into one larger CSS file. Merge our small JavaScript files into one larger JavaScript. But that comes with a penalty. We have more to download. We have more for the browser to parse, regardless of whether it uses this all or not. We have to wait for it to download it all before it can really start to use it. And when something changes, we have the challenge that we may only change 1 byte in one file, but the whole bundle is invalidated and has to be re-downloaded again. We employ similar techniques for images. So we love icons on the web. And before we rediscovered SVG, we used icon fonts. Before we loved icon fonts, we used to write tiny GIFs or tiny pings and merge them together into a single sprite. So instead of downloading tiny little images, we can merge them together so we have one larger image to download. This is quite a sort of nice sprite, a sprite scale, because if you often look at other people's sprite maps, it's not regular like this. They have their logo set on a transparent background. So every pixel of this sprite is used. But if you look at LinkedIn sprite, for example, they have a logo and they have a huge amount of transparency behind it. And to get a single sprite out of a sprite map or a sprite image, we have to download the whole thing. We have to decode the whole thing. Even if it's on a transparent background, we have to decode it all. And the challenge is that takes memory. On a mobile phone, it's not unusual for a browser to decode the sprite, extract the image, it stores it in memory. It obviously has the sprite cached on disk as well. And then as you scroll down the page, your sprite goes out of viewport, so the browser discards it. You get to further down the page and we're going to use the sprite out of the sprite map again, so the browser has to pull it back in off cache, decode the image again and extract it. So they're not free, and powerful desktop computers have sort of hidden it from us. The other thing we do is we override the browser's priorities. Browsers have an inbuilt set of priorities to what order they decide to download things in. So they'll start with HTML, then they'll start parsing the HTML to typically discover they need some CSS. Generally, people put blocking JavaScript in the head, so the next thing they start doing is downloading that JavaScript. While the browser's downloading that JavaScript, because it can't carry on parsing the HTML until it's executed the JavaScript, what it does is it has a lightweight second process that scans the rest of the document looking for other files it could download, and downloads them and prioritizes them, whether they're images that it thinks are visible, it'll give a higher priority. JavaScript, even if it's down the bottom of the page, it tends to download as a high priority. Images that aren't visible, it'll download them at low priority. So the browser has this heuristics in that they've learned from looking at millions and millions and millions of browsing sessions to decide what's the optimal order to download stuff in. And what do? We decide we know better. So we embed images as data URIs or fonts as data URIs. Which makes the download bigger and overrides their priorities. We also do things like inline critical resources. So we may choose to identify what's our critical CSS, bang it straight in the page and in the head so that the browser's got it as soon as it needs it. But of course, these aren't cacheable. Unless the data URI is in our CSS, it's not cacheable, in which case it is cacheable. But if it's in our HTML, it's not cacheable. And what this highlights is a tension between what's efficient for us as developers, how we modularize, whatever, I'll say it, get there one day, components to develop and build them, and how we need to bundle them to make them efficient to deliver over the network. And things like mod page speed and gulp and grunt and broccoli and plumber and any other build system you can think of that does concatenation help overcome this problem. But wouldn't it be great if we could use the network more efficiently? Wouldn't it be great if we could simplify some of our build processes, take some of the complexity out of that, and just rely on the protocol, on the delivery mechanism to help us deliver pages efficiently and fast? And that's where HTTP2 comes in. Now, HTTP2 originally came out of Speedy's experiment at Google. Lots of people say HTTP2 is Speedy. Those people who have a downer on Google, I would say, especially say that. But through the standardization committee, it changed quite a lot, and there were new things added, and a lot of other people contributed to it. So although Speedy proved the idea, HTTP2 is definitely a generation on from that. And what typically happens when people first start talking about HTTP2 is they show you a video. And this is the Golang example to show how much faster HTTP2 is than HTTP 1.1. Akamai have one, CDN77 built one, there are various around there. So what we do is we sit and watch the video, and it's slowed down 10 times, I think it is. And what we begin to see, of course, the HTTP2 one is really, really fast. It's finished. The other one's going to take, I think it's 3.6 seconds before it gets to the same point. So, everybody adopt HTTP2. But the real thing is, whenever somebody puts a video in front of you, whenever somebody puts a benchmark in front of you to demonstrate one point over the other, it's question them. Question whether it's really a real world example, understand how the test has been built. And if you remember about 15 minutes ago, I said HTTP 1.1 is really bad and really inefficient when it comes to downloading small files. So what they've done here is they've actually built an image that's made up of lots and lots of small files. So it actually exploits the real weakness in HTTP 1.1. Whereas because HTTP2 is slightly different, which we'll come on to, it doesn't experience the same issues. HTTP 1.1 has the round trip latency for every block of the image. It has the overhead of the headers for every block of the image. It has the thing that it can only download 6 images in parallel, which acts as a natural break. Whereas, as we'll come on to, H2 doesn't have those. So when people put these nice videos in front of you, look at them skeptically, ask them questions. So what makes H2 different? The biggest thing to think about, and the biggest thing to remember, is if you don't remember anything else from this talk, HTTP2 is a wire level protocol. At the application level, it still has get, post, head, delete, It has all the normal HTTP verbs. It has all the same it has all the same HTTP response codes. So at the best or at the worst, it just looks like HTTP 1.1. You don't have to worry about it. The difference is HTTP 1.1 is a text-based protocol, whereas HTTP 2 is a binary-based protocol. And we'll come on to that. It's multiplexed. It uses a single TCP connection and intersperses the packets for each resource all across that one connection instead of having multiple connections. It uses header compression, so we can get rid of some of that repeated header overhead, which makes life more efficient. And it has something called HTTP push, which we'll come on to, which we can exploit to make our pages load even quicker. And what happens is each request in HTTP 2 becomes something known as a stream. And this is a waterfall from WebPageTest. Looks pretty much like a HTTP 1.1 waterfall. What you might notice is these blocks here are quite long. And if you're used to reading a HTTP 1.1 waterfall, you might look suspiciously at them. It takes a while to get used to them. But you know, each request becomes a stream across our connection. And streams are divided into frames. In this case, we've got a headers frame and a data frame. So whereas in HTTP 1.1, the headers and the body are all mixed together, in H2, they're separate. They're different frames. And there are things like reset stream frame, there's push frame, there's frames to change the window size. And the frames, as I've said before, are multiplexed over a single TCP connection. So in this partial bit of a stream, the headers frame for data, for the headers frame for stream 1 will have already gone. So we've got the data for stream 1, we've got the headers for stream 2, data for stream 2, and then some more data for stream 1. And what that means is we can start to mix resources together, and the server has to determine what's the appropriate order to send those frames onto the wire. This is what it looks like from a TCP connection view. Top one is we see this is the same site in both. The funny bit at the end of the waterfall is due to the fact those final resources are loaded via JavaScript. But what we can see is this is the same page loaded, and in HTTP 2 we have one TCP connection, in HTTP 1.1 we have 6. So the real challenge is, if I'm going to send frames over a single connection, how do I, as a server or a browser, understand what's the order to send those frames? How do I prioritize them? And HTTP 2 has this prioritization scheme that's based on weights and dependencies. And what this means in this case is we've got 3 dependents on the route in the beginning. One's got a weight of 200, one's got a weight of 100, and one's got a weight of 1. And what that means is basically the one with a weight of 200 gets 2/3 of the frames, so 2/3 of the bandwidth. The one with a weight of 100 gets 1/3, and the one with a weight of 1 gets virtually nothing. It will only get frames, it'll only get time on the wire if the others become blocked for any reason. And then once the resource with ID of the stream with ID of 2 finishes, and its 2/3 is then split between the 2 resources below it. So this way of building a tree of what resources depend on each other and what priority they've got. And fortunately, there are some real problems implementing this in the wild. Chrome doesn't yet support this properly, and there are some challenges as to whether this will actually change in the spec. I think Mozilla have implemented it, but you talk to people like Alex Russell from the Chrome team and others, and they're still debating about how do you ever really implement this in a real world. The other challenge with it is, although the browser can hint its priorities, the server is free to override them on the basis that the server has more idea about what all your site visitors want than an individual browser. But you know, it starts to allow us to do some interesting things. We're not just stuck with the priorities that were set when the page started to download. They can change during download. So what we might get to a situation is, you can have a web page that starts to download, and the browser decides it's got to the end of the head, but it still doesn't have the CSS, or it doesn't have some blocking JavaScript in the head. And it can reduce the priority of the HTML. It says, this isn't as important to me now. I want you to prioritize the CSS or the blocking JavaScript. So it can start to do clever things like that to alter the priorities as it goes along, so at a point in time it can indicate what's crucial to it. We've got header compression, as I said, and it uses HPAC, and the spec is there. And what it has is a fixed dictionary, so things that appear on every request are at the start of the dictionary. So things like the path, user agent, and a few others. And then things that might change between requests, it stores in a dynamic dictionary. But it just reduces overall the amount of headers it needs to download. So the real question is, does it make any difference? Now, for this test, I used some shonky HTML5 template that I've been using for too long to do this test. It's got about 40 resources on it. So it's a real page. And what I did in this situation is I hosted the page in Ireland, and I ran it from a WebPageTest agent in Singapore. So about 150 milliseconds round trip time. And when we play it, at quarter speed, or when you do this in front of clients, you show them their site going this slow, it's fabulous because they all think, is our site really that slow? So what you can see is the HTTP2 one started rendering first. And it will reach its final state in 4.6 seconds, and you know, the HTTP 1.11 still has to catch up. And if we look at how long it actually takes to catch up, it takes another couple seconds to reach the same state. You know, I think it's 6.6 seconds. So we took 2 seconds out of the page load time in this situation, just by changing protocols. I didn't change any more than that. No optimizations. There's gzip on here. There's a large initial congestion window. There's no concatenation. There's no minification going on. So it makes a 2-second difference. But nobody's asked me, because 10 minutes ago I said, if anybody ever shows you a video of a side-by-side test, ask them questions. And you know, at this point you should say, well, Andy, that's really great, but although I host my web servers in the UK, my customers are in the UK rather than Singapore. My customers are close. They're not far, far away. This isn't a realistic test case for me. So I did another one. And in this case, what I did is I hosted in Dublin and tested from Dublin. And what we'll see is, you know, when we get there is the HTTP 1.11 starts slightly ahead. It starts to render the page first. What I should really do with this test is, for those of you who don't know, if you use WebPageTest and it takes desktop videos, the video frames are shot at 1/10 of a second intervals. So there could actually only be 1 millisecond difference between these two when they're starting to draw. You can't really tell. But you know, in this situation, the HTTP 1.11 gets there first. But what we find is when we get to the end, the H2 one catches up, and they finish at roughly the same point in time. The other great thing that's happened here is the HTTP 1.11 is over an unsecure connection. Although H2 doesn't demand a TLS-based connection as a secure connection, none of the browsers will support it over an unencrypted connection. So what we've actually done on the bottom one as well is we've added the TLS negotiation. So we've delivered it on a secure site, and we've overcome the overcome the overhead of making that secure connection using HTTP2. So it's given us a secure one, and it's given it in the same amount of time. But these are sort of artificial test cases. These are test cases. What happens in the real world? Unfortunately, Patrick Hammond talked about exactly this yesterday at Smashing Conf. So I haven't stolen his slides, I've borrowed his slides. Because I've known they've been doing this for ages. And I did have a slightly different FT slide in here before, but what we can see is that this is the load time. So in load time in the real world, that for the FT, and the FT were just delivering their images over HTTP2 and the base site over HTTP1. I don't know whether they still are. I suspect they've moved on from that slightly. Is that in the real world, on mobile, H2 is delivering a faster experience to their FT's mobile customers. It's the same on tablet. Well, the tablet's slightly slower. And on desktop, for various reasons, whether it's the quality of desktop connections, fixed line connections, where it's the power of the desktop devices, they're roughly the same. More interesting comes back to reflect the test I did on latency. And you can think of this as the double-in. Oh, no, sorry. Come around this way. If you think of this as sort of the double-in situation, and this is the Singapore situation, what we begin to see is that on fast connections, H2 makes less difference. But on slower connections, it begins to make more of a difference. And finally, the other chart Patrick came up with is looking at when the page starts to render. And in all situations, HTTP2 allows their page to start rendering more quickly. And at this point in time, I believe they're not optimizing differently between the two of them. They're delivering the same content to H1, H2. So it makes a difference in the real world.
And was the first one page load time?
Yes, this is page load time. I'll put the slides up later anyway, but Patrick's slides are well worth a good look through. Whether Vitaly releases the videos of Smashing Mag conferences, I don't know. But I suspect the talk's well worth a good look at as well.
Your test was different, wasn't it?
Well, in what way is my test?
Your test had HTTP1 loading quicker, like initial load quicker.
So in this one, in this test here, so when they're really, so if we go back to this one, in the test, in the Singapore to Ireland test, HTTP2 was faster. It started rendering more quickly, I believe. You can try it, look. Yeah, so the HT1 starts to render more quickly, slightly more quickly in this case. And it obviously finishes render more quickly than the HTTP 1.11. So in this test, so Ireland to Singapore, H2 is faster in both aspects. In the Ireland test, what we find is H1 starts to render slightly more quickly. We're talking about a tenth of a second between those frames. So not much. And then the H2 beats it at the end. The reason I suspect in this situation why the H1 begins to render quickly is because it doesn't have the cost of doing the TLS negotiation to make a secure connection. But this is a point test, whereas what the FT have got is a test that looks across their whole population of readers. Now, their reader population is something like 300,000 a day or something like that. It's got in newspaper terms, it's got a relatively low reader population because it's subscription, but what they've got is high intensity and keen readers who read it regularly, read it daily, read it globally. So this is looking across their whole population. So this is the 95th percentile. So what we can say is that 95% of people who visited their site had, in the first case, on mobile, had a load time of less than 10.76 seconds. And that's the big difference between my tests. My tests are a single point in time that repeated many, many times, whereas this is over a big population. And in all cases, they're faster. What we don't see is we don't know how many points are in this. So this is the median. So this is the 50 percentile. So what they've done is looked at everybody visited their site, measured them all, and split them in half and found where the middle is when you rank them. And even in the UK, so average 3G latency is 300 milliseconds. It used to be 600, but it's now 300. 4G used to be about 48 milliseconds. It's now getting up towards 100. As more people go into 4G, 4G gets slower. Exactly the same thing happened in America. So it didn't come as a surprise to us. So, what we're seeing is that in the FT's tests, or the FT's real-world numbers and my tests, show that there's basically no penalty from using HTTP2 and getting the added benefit of going secure. And where you're over a longer latency connection, you actually get a benefit. Akamai's own numbers show just the raw improvement of using HTTP2 is anywhere from a 5% slowdown to a 20% speed up. That's the range. And most people aren't optimizing for it yet, and we're still learning how to deploy it, as we'll come on to. So, H2 also gives us some new opportunities for optimizations. First one of these is server push. So, at the moment when we request a page from a web server, the network sits idle while the web server creates the page and then sends it back to us. But often that web server has some idea of what other resources need to go with that page, what CSS we want, what JavaScript we want. And what we can do with H2 is we can decide to push the critical resources. We can decide that as a server, I know you're going to need this CSS. I'll push this CSS out to you before we've even finished building the page to send to them. And then we'll send the remains of the page out. The browser will start to parse it and use it. The browser can actually reject the push request if it's already got the resource or if it doesn't want it. That's the theory. In practice, what actually happens is it ends up at the browser probably before the browser realizes it wants to cancel it. But it's just a way of short-circuiting the time we take to build the page. There are some other resources that are really handy to push. So one of the challenges with fonts and background images in CSS is a browser doesn't discover it needs them until it's downloaded the HTML page, downloaded the CSS, started to construct the CSS object model, looked at the nodes on the page, worked out what styles apply to those nodes, and worked out if a style that's got a font or a background image applies, and then it can request a download. So what we could do in a push situation is we can push the font or push a background image before the browser realizes it needs it. The other thing is multiplexing starts to offer some interesting possibilities too. And John Mellor of Google did some experiments a few years back, and this was simulating Speedy. And he was looking at if we use progressive JPEGs, so JPEGs that start to render as we get the bytes for them instead of waiting for all the bytes to render for them. If instead of downloading this JPEG, then this JPEG, this JPEG, this JPEG, what if we took a bit of each JPEG, downloaded them and started to render them on the page? And what he looked at the BBC site and he looked at how much of a byte of an image do you need to make a page useful. And the one on your left is the equivalent of HTTP 1.1, and the one on the right is the equivalent of H2. And we can see that even with only 5% of image bytes downloaded, the H2 one has got more detail in its images. It's only marginal at the moment. By the time we get down to 15% of the bytes, the H2 page is beginning to look reasonably complete. If we look at some of the things like, this guy here is still blocky, Andy Murray is still quite blocky up here, but we've got to start to get representation of the images, whereas we don't even have the images over the other side. By the time we get to 25% of the bytes, the H2 one looks pretty much done, whereas the H1 is still lots of blank spaces. And it actually takes until 80% of the bytes have been downloaded in the H1 world for it to look the equivalent of the H2 one at 25%. So multiplexing allows us to deliver a visual experience to our users more quickly. There are a few questions over whether we like progressive images. There was a study done, but it's a very small cohort was in the study. And there are some questions about whether we like them or not from a user experience perspective. But I think that study sort of needs redoing. The question is, when can we start to use it? When can we kill off some of these HTTP 1.1 techniques that have an overhead? Well, the good news is browsers have pretty good support for it. I can't remember what the can I use number is, but if you consider Chrome 40 supports it, and I think Canary's 50 something now. Edge will one day appear. Firefox supports it. Opera supports it. Safari supports it, with the exception of push. It's a pretty good spread of modern browsers that support it. We actually saw quite a big jump when iOS 9 rolled out with HTTP2 support of people who were capable of using it. Of course, browsers are only one half of the equation. We have servers too. And the server story has got better and better. For a long time, the people who really supported it are things like Google with GFE, Akamai with Ghost. And then Nginx rolled out support, Apache rolled out support. Neither of those two support server push yet. And there's a whole class of new servers that have come out. There's things like Caddy, which makes it really easy to deploy TLS and has integrated Let's Encrypt built in. Doesn't support server push, but there are some web servers out of Japan, like H2O, which I tend to use, or NGHTTP2, and a few others that are well-featured small servers that are great to play with. And HTTP2 support gets better and better. So you can deploy it today on Google App Engine. You can deploy it on Nginx if you wanted, if you don't want server push. Apache using mod HTTP2. You can deploy this stuff in the real world today. But you've got to pick your servers carefully. And they really need to support the stream and connection flow to make sure the right bytes are going down the wire. Some of them don't support dependency weights, but supporting dependencies is important. A couple of years ago, I was doing a talk in New York, and it was on Speedy at the time. And I'd done some similar tests about 6 months before for another talk using Chrome and Mod Speedy. And my tests were 20% fast. It was great. And I did the retesting for this talk I was going to do in New York, and all my tests were slower. Because what happened at a point in time is Chrome went from actually controlling the order it made the requests over the wire to just saying, these are my priorities, server, fulfill them. And Mod Speedy never fulfilled them. Mod Speedy just pulled the resources off the disk and sent them down the wire in whatever order it happened to find them. So I went from this page where normally you got the HTML, the 3 JavaScript, jQuery, and a few other things, to I'd get the HTML page, then I get jQuery, then I get an image, then I get some more JavaScript, and eventually my CSS was 6th and 7th down the line, so the page was horrible. But we come across the other thing is, does it support server push? That's very much immature at the moment. And one of the things to look for is how does it help optimize? Some of the servers like Jetty, for example, look at requests as they come in and look at when somebody requests this HTML page, they seem to request this CSS as well. So what I'm going to do automatically is push them the CSS. I'm going to make the decision for them. But it's not all smooth sailing. Implementations are still young. This was H2O 1.52, I think it was. And I pushed 3 CSS files, 3 JavaScript files, and the font. And when I actually looked what was actually happening on the wire, the font arrived first, because the server was pushing the font first. And then the 3 JavaScript files, and then the 3 CSS, exactly the order I didn't want them to arrive. It got fixed in H2O 1.3. Khan Academy wrote about the way they, on their homepage, they had 250-something JavaScript files, and they unbundled it all, and it was slower. Now, they had this 2% loss due to the fact that when we bundle things, gzip can compress them better because there's more repetition. But the demands we're placing on servers are changing. So, browsers make 6 requests. Those connections are used, and then when one request is complete, they make another one. So the server sort of has this dribble of requests from the client through. All of a sudden, in the HTTP2 world, we've got the fact that Khan Academy send 251 requests to the server at the same time, and the server has to track them and work them out. And there are some issues with GAE coping with that amount that will get sorted. I did some tests with server push You know, and this isn't Chrome. And look, isn't this great? With server push, my page loaded 0.3 of a second faster until I tested it in Firefox, and there was no difference. And the challenge here is actually a bug, a delay in Chrome while it starts the preloader. And what's happening is it's about 1/3 of a second after finishing parsing the HTML before the browser starts to preload it to look for the other resources that it wants to download. And what I was doing with push is overcoming that bug and having the resources already waiting for the browser when it needed them. This will get fixed. But you know, how can we start to debug this stuff? If we use WebPageTest and we've got push on, you know, in the panel when we look at resource, it shows us what's being pushed. It only used to work for Firefox. As of about the last week, it works for Chrome too, so we can see what we're being pushed. We can see the browsers recognize it as a push. If you want to get really nerdy, the other way to go is to use Chrome net internals. And it's massively powerful, and you can capture some events, and then you can filter by type HTTP2, and you can see how Chrome interprets your HTTP2 traffic. And you can see what a GET request looks like under HTTP2. So we can see we're sending some headers to the server in this case. And it looks very similar to HTTP 1.1 request. You know, we've got the method, we've got a path, we've got a scheme, which is new to H2. The other thing to notice in H2 is the H2 headers have a colon on the front of them to differentiate them. We can see when we received headers back from the server. We can see when we received a data frame. We can see when a server decided to push a resource. And this is the way I check push most of the time, is looking net internals to see, you know, we got a push from the server. And then sometime later, we'll hopefully see push request or push stream adopted. So this tells us that Chrome's decided, okay, you've pushed me this resource, and I've actually decided I want to use it. Because until the browser adopts the push resource, it sits in memory. It doesn't end up in cache, doesn't get written to cache on disk until the browser's decided it actually wants to use it. But this is, it's all right if you're a nerd and want to dig through this stuff. But you know, we want stuff like this. So Rebecca Murphy, she worked for Bizarre Voice back then. She agreed to go to Paris and do a talk on HTTP2, and I had a call with her about 2 weeks before going, Andy, I don't understand all this stuff. It all appears broken. I said, don't worry, yes, it is broken for lots of it. And so Rebecca wrote this. I was trying to do something similar with the raw JSON, but Rebecca got there faster. And this is on GitHub, and all you do is you capture the events for a HTTP2 session in net internals, copy and paste it into a text file and run it through this. And what you begin to see is you begin to get a visualization of what's going on across the streams on the wire. So we can see things like where we did a push request in this situation and where it was accepted. This is obviously one of my very broken waterfalls I noticed this afternoon, is because we do a push request, we get accepted, and then we receive headers back here, which is a long way out, whereas what we'd normally expect to see is a push request and then receive the headers. I think this is where I showed the waterfall where the push was broken. I think this is the waterfall from it, because what we see is we get the font, it's pushed, we receive the headers, we get data for it, and what we see is we receive the push for, say, CSS here, and then we get the data further down. So it helps us to get a visualization of what's going on the wire, and visualization is really powerful. I've been hacking away for about 3 months on and off to build this into Chrome Net internals, and one day I will finish, and my friends at Google will stop nagging me. There are things like the client of NGHP2, which you can use to point at your server and pull the data down and see what's going on. There are other tools out there that you can check how good your server is with H2Spec, which I can't remember whether it's written in Go or C. I think it's C. And you know, on the left-hand side is running against H2O. On the right-hand side, it's actually running against Akamai. This is about 3 months old, so I hope Akamai is a bit better than this now. But you know, it's a conformance suite. It's a way of testing what's going on. And you can see that Akamai end up with lots of red and yellow, whereas H2O ends up with none. So we're starting to get tools out there that allow us to verify the quality of these new servers that are coming across. If you're missing Telnet for debugging, you can use Brad Fitzgerald's, what's it called? I can't remember what it's called. HTTP2 utility that allows you to, so in a HTTP 1.1 world, you can telnet to your web server. You can issue it a GET, just type it in your terminal and it will respond back to you. You can't do that in a H2 world, and this allows you to do roughly the same thing. One of the key things that's important though is good, efficient TLS, setting up secure connections efficiently. So it's things like short certificate streams, large congestion windows, using session resumption in HTTP and in TLS, certificate stapling. TLS 1.3 that's coming has this situation where it can negotiate a secure connection in 0 to 1 round trips, as opposed to at least 1 round to 2 round trips we need at the moment. So that will make it even quicker. But implementing TLS efficiently is really, really important for HTTP2, because until that connection's created, you can't request anything from the server. If you want to know more about TLS, Elia runs a site called Is It Fast Yet? It contains lots of stuff. Even Ristic's book is the Bible. If you've never bought this book and you do TLS stuff, you should. And Qualis's SSL Labs is the way I test every TLS deployment I ever do to see what issues it's got and see how well I've got it. So our challenge is, we're living in a mixed world at the moment. A large proportion of our clients can support HTTP2. Some of them will always be HTTP 1.1. So how do we deal with that? And lots of our current good practices remain good practices. So things like shrinking content, whether it's gzip compression, minification, optimizing images, reducing the number of redirects we make, because redirects are round trip to say, no, you didn't want that, you wanted this instead. And it's not unusual to see redirect chains of 5 or 6 sometimes. Efficient caching, so we reduce the need to download it at all. Using a CDN to reduce that latency to make things closer to us. And just reducing the number of DNS lookups we've got to do, or the number of TCP connections we're using by going to third parties. Some things are going to vary. In general, we should replace inlining stuff with server push instead. Some people say don't use concatenation anymore. Don't merge CSS, don't merge JavaScript together, and don't use image spriting. It's going to become more subtle rather than the black and white. YouTube have got this interesting situation at the moment where what they found in image spriting is they took out all their image sprites in tests, which made the first page download really quickly, but then had an impact on a second page somebody went to, because normally that sprite would be in cache so they can extract the image. The other area they see an issue is if you have a sprite that you do a rollover effect on using bitmap images, and when you do the rollover, the browser suddenly realizes, oh, I need this other image. I need to go to the server and get it. Now, I argue, and I think most would argue, you should use SVG in that world and use CSS to start it. But there are situations in which you may still want to use image sprites. And generally avoid sharding. We tell people these days to only use 2 shards anyway, not use 4 because of packet loss situations. So stick to 2 shards. And HTTP2 will do something really interesting with sharding. That if you have 2 shards, so 2 host names that resolve to the same IP address and are protected by the same certificate, then HTTP2 will coalesce them into a single connection. So what we see here is we've got 2 host names, they resolve to the same IP address. And what we see on the second connection is we've done a DNS lookup to resolve the name, but we haven't made a new connection. It's reused the existing connection. There are some challenges in practice, because things like global load balancing, which large sites use, mean that people don't go to the same IP address, so it may not always work. But we've still got plenty of challenges. We've still got, what do we do about CSS import? How do we deliver content intelligently to different devices? And this is where people are looking at dividing traffic by protocol, so sending HTTP 1.1 traffic to one set of servers, HTTP 2 to another, using an automated service like Akamai's Ion or Radware's Box, or whatever it's called, to optimize on the fly depending on the protocols somebody's using. Peter Muller's doing some stuff with a tool called Fusile, where it's a file system that optimizes. So you just deploy your website, and this file system deals with delivering the optimized version to the client. We've also got the challenge of third parties. And this is a real site. And it makes 160 requests, of which 47 come from the origin. The rest all come from other third parties. There's 53 redirects in there, and 44 domains involved. And while HTTP2 in this world would help with the stuff that comes from the origin, it really doesn't help with the number of small requests we're making for third parties. And third parties remain a challenge, even in the HTTP2 world. There are some things we can do to help. So the WC resource hints can help speed up the requests from those third parties. The first one says, resolve this DNS before, this host name before I use it. The second one says, resolve this host name to its IP address and make a connection before I use it. And the last one basically says, I'm going to use this resource, I want you to download it. So it's really handy for telling the browser about the critical resources you want to download from other people before the browser discovers it. If you want to learn more about HTTP2, there's the excerpt from Ilya's book, or Daniel Steinberg and Mozilla wrote HTTP2 Explained, that are both on the web, that go into it in quite a lot of detail. But the biggest thing I'd encourage you to do is go and play, go and explore. It took us till 2006, I think it was, when Steve Souders wrote his first book, to understand how we can make the most of HTTP 1.1, how we delivered sites efficiently over it. And, you know, we really don't want to wait 10 years before we learn how to use HTTP2. It's coming. People are deploying it today. There are lots of opportunities in there. You know, the new optimizations using multiplexing that will help sites load faster, using push to prioritize resources down there. It changes the way we build sites. And the best thing we can all do is go play, go learn, and share what we learn. Thank you.